like this. Once we are asked to do that, you would immediately have to write approximate f of x plus f prime of x dx. And you know that the next step would be to identify the function, to identify x, to identify dx, and of course calculate f prime of x. So I'm ready when you are. What is the function here? Yes, the function is indeed tangent x. Good. And I can find its derivative, secant squared x. What is x? Something that we know. X is, very good. X is 0. We know nothing about 3. So then dx is 3 degrees, which is 3 multiplied by pi over 180, because in here it has to be in radians. Inside a function, it doesn't matter if it's 0 degrees or 0 radians or pi over 6 or 30 degrees. So this will be pi divided by 90. I'm sorry, 60, of course. Very good. So now we're ready to write tangent 3 degrees is approximately f of x, which means f of 0. How much is tangent of 0? Very good, awesome. Plus secant squared 0 times pi over 60. Now we have to identify secant 0. Secant 0 is 1 over cosine 0. But cosine 0 is 1. So then secant squared is 1. So then the answer is pi over 60. Of course, you are not supposed to do anything, but you are supposed to check just to make sure that this is indeed correct. So when you plug in tangent, if you plug in 3 degrees, that you have to make sure that that the mode is in degrees. So then tangent 3 degrees. And then pi over 60 doesn't matter what you have. It's still pi over 60. So the approximation is quite good. I'm sure you had no idea that you will be able to, at any point in time, come up with an answer for tangent 3 degrees. And a very good answer at that. Perfect. Very good question. Thank you for that. Next question. Anything else that you would like to go back to? Anything else? Is there a particular type of problem that you would like us to go back and look at? Any particular type of problem? Anything? Yes, what does it say?
Y equal to tangent, y equal to tangent x squared, and then cosine h x.
Tangent?
H squared.
Oh.
Times yeah, squared. And then
Oh, so it's hyperbolic tangent squared x.
And cosine hyperbolic x.
Is it times?
Not x there.
There's no x.
Oh,
Cosine hyperbolic.
okay, so this is the function that we want to differentiate. Very good, let's do that. So remember there are several functions in here. The first function is the power. The next function is tangent. And the next function is cotangent. Of course, hyperbolic tangent, hyperbolic cotangent. So when we differentiate, we start from the outer. By differentiating the power, we bring down 2, hyperbolic tangent, we subtract 1 from the power. Now we have to differentiate tangent, hyperbolic tangent, which is times hyperbolic secant squared of cosine, make sure it's cosine, hyperbolic cosine. And now I have to multiply by the inner function prime, and we know that this is hyperbolic sine. Correct. Very good.
So the hyperbolic.
Yes?
Two different from what we thought. Right?
Hyperbolic functions are all combinations of exponential functions. Yes. Hyperbolic sine is e to the x minus e to negative x over 2, and hyperbolic cosine is the same but plus. So there are 2 functions that were determined using exponential, e to the x. The natural exponential, not just any exponential, the natural exponential function. So what would you like to do? I'm waiting for you to ask anything.
Can you use some of the arc into it?
Some of the?
The arc. Like arc sine, arc
Inverse
cosine.
square.
Oh, yes. Yes. Very good. So let's take a look. What about 38 on page 265? And that is y equals arc tangent of arc sine of the square of x. Is that what you had in mind? Yes? Perfect. So let's take 1 minute. I had another glitch with the computer. I had to restart because there were like 7 gig already in there. I couldn't delete them. I mean, I deleted them, but they were still like they had a patina in there or something, like a remainder. I'm not really sure how to explain it. That's why I'm opening all my windows now, because I had to reboot them only. Okay, are we ready? So when we differentiate this function, arctangent is 1 over 1 plus this squared. Arc sine the square of x squared times arc sine prime, 1 over the square root of 1 minus this squared, it happens to be x, times the inner function prime, 1 over 2 the square of x. No, you don't have to do anything to it.
So what would arc secant squared look like?
Is our secant squared? There is nothing. I can't do anything. I have to determine the square root of x. I have to apply arc sine. You meant our secant. Oh, you mean r sine? You wanted to look at arc secant?
Yeah.
Oh, okay. Oh, I'm sorry, I misunderstood. I thought you were talking about arc sine. My apologies. So, if you remember, I also mentioned that only arc sine, arc cosine, and arc tangent are what we're interested in. But if you want to go to arc secant, we can. But then I have to give you the formula. So I'm not really interested. I'm interested to test the basic knowledge. Because if you know how to address this, you can look up a formula and plug it in. Very good. Anything else?
For number 2.
Yes? Yes?
For A, how do we like put 2 into the
I didn't read another formula.
for 2, like what is it function?
We did.
Okay.
No, no, we're asked to find the velocity of time t. We didn't. Yeah, that's okay. Maybe because I wrote 2 points on the side and you probably thought that we have to plug in 2 or something. Good, very good questions. Anything else? Okay, what I would like to do then, I would like to list the topics, and then you'll tell me if you're comfortable with everything, and then if you are, then we can continue with something else. If you're not, then we'll practice. Okay, so differentiation rules for all types of functions. Product rule, quotient, chain, trig functions, plus limits, of course, implicit differentiation, okay, that's 3.6. 3.6, applying logarithmic differentiation. Motion, you know, the particle, etc., etc. Linear approximations and linearization. And 3 hyperbolic functions. Of course, related rates. That's it. So look at these topics and see if we need anything else.
Can we go over the one with the limits?
You mean trig functions?
The limits?
Yes. So let me make one up. Let's say limit as x approaches 1 from sine x minus 1 over x squared minus 1. When we calculate limits, the first thing we have to do is to identify what it is. Because if I plug in 1 and I get 15, I'm done. I don't have to do anything. But in this case, when I plug in 1, I get 0 over 0. So I know that there is hope. There is no guarantee, but there is hope that the limit exists. I have several options here. One is apply L'Hopital's rule, because it's a ratio. And I can apply L'Hopital's rule. There is no product here, so I shouldn't have any difficulties. The second one is to remember, this is a very important result. As long as all these are the same. And of course, this means x minus 1 approaches 0. You subtract 1 from both sides, and x approaches 1 means x minus 1 approaches 0. So one option is L'Hopital's rule, the second option is this. Which one would you like to apply?
Like, how do you know like which one to apply?
Both work.
How do you know which one to research?
Well, in this case, because it's not a product, top and bottom are not products, especially of trig functions, I will apply L'Hopital's rule.
Yeah, can we do both?
Yes, of course. So if you want to apply L'Hopital's rule, then you will differentiate the numerator and differentiate the denominator, and this is allowed only inside the limit, never again. So then limit as x approaches 1. When I differentiate sign, what do I get? Yes, cosine of x minus 1, but I have to differentiate the inner function because it's not plain x. But it happens that x minus 1 prime is 1. So now I differentiate the denominator and I get 2x. At this point, I'm done. Because there is no more 0 over 0. I would not even be able to continue with L'Hopital's rule because it's not 0 over 0 anymore. The numerator is cosine 0, which is very good, 1. And the denominator is 2 times 1, which is 2. So it's done. Now, if you want to apply this method, then you will have limit as x approaches 1 from sine x minus 1 over x plus 1, x minus 1. And now it happens, oops, I didn't mean that. X minus 1 approaches 0. That's what I wanted to write. So it happens that you have that box that I've been talking about. Meaning what? Meaning this. Which means that all this will approach exactly. So now when you plug in 1, you get 1/2. So basically they're the same. There is, just one step basically in both. You just have to factor the denominator and just realize that when x approaches 1, actually x minus 1 approaches 0, and all these three quantities are the same. This quantity will be 1. And then when you plug in 1 over x plus 1, you get 1/2. Anything else? Yes, please. Elizabeth?
For hyperbolic functions, are there limits to that?
No. No, we haven't looked at any limits. There is nothing in your book. Let me take a look. Very good question. If there is something, you will have to change it into e to the x. Yeah. So let me look. I need maybe, yes, I see some limits. Yes, I see some limits. Let's just work on some. Yeah. Good point. Thank you very much. Thank you. Here they are. So choose any one. We're going to change it into e to the x and determine the limit. Which one? F. Cotangent. Okay. There's no need for cotangent, but if you want cotangent it is. Because it's 1 over tangent. That's the only reason. But that's fine. It's the same. So we were looking at limit of hyperbolic cotangent x when x approaches infinity. Okay, so what we know is this is limit as x approaches infinity from 1 over tangent, hyperbolic. So this is 1 over hyperbolic tangent, which we know is hyperbolic sine, or if you want, you can just write hyperbolic cosine. Yeah, the same thing. Same thing. X approaches infinity, so it's e to the x plus e to negative x over e to the x minus e to negative x. Because at the top we have cosine, and cosine is e to the x plus e to negative x over 2, and this is e to the x minus e to negative x over 2, and when I flip, the 2's go away. That's why I was getting to tangent, because we looked at tangent as being the multiplicative inverse. That's why I continued with tangent. So then, we had this before. We didn't know that it was a ratio of two hyperbolic functions, but we had this before, and what did we do? Well, obviously when x approaches infinity, where does this go? Right? It's 1 over. And x approaches infinity. Where does this one go? Right. So then it's e to the x over e to the x. You could use L'Hopital's rule. I don't recommend it here because it's possible, I haven't checked, I haven't tried it, but it's possible that we're going to go around in circles because these e to the x don't go away. So they will always be there because e to the x prime is e to the x. E to negative x prime is negative e to negative x. So I don't recommend it. But what we did in the past, if you remember, we factored out e to the x. Because x approaches infinity. Otherwise, I would have done something else, possibly. So what is left in parentheses? Obviously 1 plus and 1 minus, but what? Yes, because it's negative x minus x, which is negative 2x, and e to negative 2x. These go away. So now let's see where this is going and where this is going. When x approaches infinity, this goes to yes, and this goes to yes. So the answer is 1. So the limit of hyperbolic cotangent x when x approaches infinity is 1. We did not graph hyperbolic cotangent. We don't know how it looks like. We can if you want. Very good. Anything else? Anything else? I'm hoping you're going to review everything between now and Monday, and you're going to ask more questions on Monday then. Yes? And you're going to finish your web assign. When I write the test, which I did not yet, I'm going to look at your problems. I think problems in web assign, many of them are even easier than the ones in the book. Would you say that, or you would disagree? Or pretty similar? Similar? Easier? Yes, I think so too. So that I'm going to use easier problems. Anything else? Okay, you allow me to start chapter 4. Yes? Chapter 4 is not going to be on this test, of course. In chapter 4, we are going to look at 9 sections. The last section will be connected to chapter 4. To test 4, I'm sorry. So let's see what we studied in chapter 2. Anyone remembers what we studied in chapter 2? Limits, exactly. Yes, because we needed to find the derivative, and the derivative is a limit. Okay. What else? Tangents, right? What else? Velocities. What else? Pretty much limits, right? That's even the title of the chapter. Okay, what did we study in chapter 3? Yes, we looked at derivative, as rules, differentiation rules. We looked at logarithmic differentiation. We looked at word problems like related rates or motion problems, right? So in chapter 4, we are going to look at applications of differentiation. So the title is chapter 4, Applications of Differentiation. Nine sections. The last section of this chapter, which is, I think I'm wrong, I think it's 10 sections. And the last section, which is 411, will be connected to, I just want to verify my memory, antiderivatives. I'm completely wrong. Completely wrong. So there are 8 sections. And 4.9 will be connected to chapter 5. This chapter 3 had 11 sections. Chapter 4 has 9 sections. But the last section will be connected to chapter 5, which means test 4. Okay. The first section, which is 4.1, deals with max-min of functions. And we know that we have really 2 types. We have what is called relative or local, I'll explain in a minute, or absolute or global. Some books use absolute, some books use global, some use relative, some use local. They are identical. These two are identical, these two are identical. So what is the difference between the two? So let's graph a function. We're done for now with our best friend, so it's going to be a different function. So let's say we have this. Obviously, this function has an absolute max here. There is no other value higher than it. Obviously, right here, this function has what? Absolute minimum. Or global minimum. Absolute max, absolute min, global min. Also at these 2 points, this function, because it exists on both sides, and all function values are smaller on both sides than this value, this is the highest, and all these values are smaller, this is also called a local max. For example, at the endpoint of the interval, I cannot show the open interval because the function does not exist on this side. So the endpoint of the interval is never local. Never local. Can it be absolute? Yes, I'm going to give an example in which is the absolute. But it can never be local or relative. Is this also a local minimum? Yes, because I can show the open interval where the function values are larger than that value. Is this local? No. Is this absolute? No, because, and this is not absolute either, because this is the absolute, the maximum possible value, and this is the minimum possible value. Now, what I would like to look at for a minute is at some graphs in your book. Right here. Please choose any graph you want, 3, 4, 5, 6. It says use the graph to state the absolute and local max, min values of each function. Which one? 6. We want to look at 6. Very good. So you agree that this point does not exist. I think I changed the problem, right? So as you see, this point does not exist. If I cannot give you the maximum, if I say it's close to, there is no maximum there. I have to be able to tell you the maximum is 5 or the maximum is -3. So this cannot be a point where the function has a absolute max. So there is no absolute max. I can't identify it. I don't know what it is because I don't know. This is 1, 2, 3, 4, 5, and I'll say it's 4.9, and you'll say no, it's 4.99, and somebody else will say no, it's 4.9999, and somebody else will. So there is no absolute max. So what about this point? Again, the same thing. There is no local min here because I cannot give it to you. I have to be able to say the local minimum is 15, but I can't. Now this is indeed a local max because I can show the open interval around it. The function values are smaller, and I will be reading 1, 2, 3, 4. Where it is at 3. When x is 3, the maximum is 4. This is also a relative or local, but also absolute. There is no other value for this function that is smaller than it. The function value exists. So when x is 4, the minimum is 1. So this is indeed a local minimum and also a global minimum or absolute. This point up here, so this was 2, 3, 4, 5, 6. At x equals 6, the y value is 3. It is a local max. I can show the open interval. This point is nothing. It's not local because it's at the endpoint of the interval. It's not absolute min because there is another value or values smaller. There is no absolute max because there are other values that are bigger than it. Any questions on this problem? Is it clear? Very good. Yes?
Number 6 on that point that
Yes?
x equals 2, can that be anything? Can it be an a local in any?
No. No, because it cannot be local unless I show the open interval. So this point I cannot show the open interval. And this point I cannot identify. I will say it's 3.1, and you'll say no, it's 3.01, and somebody else will say no, it's 3.00001, and then we'll argue forever because there is no number. Is that okay? Perfect. Very good question. So if the function is not continuous at that point, I cannot show the open interval. So it will not be a local. And hence it will not be an absolute. However, if it is at the endpoint of the interval, it can be absolute. I don't have to show the open interval. So for example, in this situation, very good question. This function has an absolute max and has an absolute min. But it does not have a local max and it does not have a local min at all. Because here I cannot show the open interval and here I cannot show the open interval. So at the endpoints of the interval, the function can have absolutes, but it cannot have local. Very good question. Okay. Next topic right here, right now, is critical number or numbers. What does this mean? Well, critical numbers of a function come from two sources. A function does not have to have critical numbers. You may have critical numbers coming from one source or the other or both, but it doesn't have to have critical numbers at all. So they can be from f prime of x is undefined, where f of x is defined. And the other source is f prime of x equals 0. So x values that make the derivative undefined where the function is defined account for critical numbers. X values that solve this equation count for critical numbers. Now, first of all, why are we looking for critical numbers? So here is the note. Only critical numbers, Cn or Cn's, can turn into max-min. If a function has no critical numbers, it will never have a max or a min. If a function has critical numbers, is there a guarantee that it has max-min? No, still no. Something else follows that we have to check. So if a function has critical numbers, it doesn't necessarily say that it has max-min. Potentially, it may have. But if it has no critical numbers, we know for sure it has no max-min. Do you have an example for me of a function that does not have max-min? Think about graphs and say this one does not have max-min. It never turns, in other words. Which one? Linear function is a good one. Exponential is a good one. I would like to look at this. So in both situations, I have to determine the derivative. So let's find the derivative, which is perfect. And then, is the derivative ever undefined? No, it's a polynomial. So this function cannot have critical numbers coming from this source. Not possible, because this is always defined. But it may have critical numbers coming from f prime of x equals 0, the second potential source, in which I have 3x squared equals 0. And from here I get two solutions, but basically one, which is x equals 0. So this is the critical number. The only critical number of this function. Now the question is, will this represent a max or a min? It all depends on the sign of the derivative. So what is the sign of this derivative? No matter what x is. Yes, the first derivative is always greater than 0. So because it does not change sign, and we'll write this down in a minute, we'll analyze other functions, then we know there is no, although it has a critical number, it does not have a max-min. Remember the graph of x cubed. So here's the graph of x cubed. Does it turn? It has a critical number, but it doesn't have a turn. Why? What is the sign of the derivative at all points? The sign of the slope of the tangent. Always positive. That's why. It's always increasing. How can it have a max-min if it's always increasing? A function will have a max-min if it has increasing, decreasing. Here the slope is positive. Here the slope is 0. Here the slope is negative. Here the slope is, and here the slope is. So it has a critical number, but this derivative does not change sign. So, conclusion before we look at problems. A critical number becomes a max-min, a point of max-min, you know what I mean? If, and here are the possibilities. So let's say x equals a is a critical number, and here are the options. At this point, x equals a, the derivative is negative, positive. The derivative is positive, negative, where the derivative is 0 and 0, or undefined, but it changes sign. So, let me say this one more time. Critical numbers come from two sources, where the derivative is undefined at this point, undefined, or where the derivative is 0. But the function is defined at a, but the derivative is not. We'll look at an example in a minute. So when the function has a critical number and the derivative is 0, if the derivative does not change sign, that a will not produce a minimum. Less than 0, 0, greater than 0. So this will be a minimum. This one will be greater than 0, positive, 0, and negative. So this is a maximum. Of course, this is a minimum, and this is a maximum. You could possibly say, how is it possible that the derivative does not exist at that point, but the function has a min or a max? Very good question, I'm going to say. And look at the example we just picked and looked at. We looked at problem 6, correct? What is the problem with this? It's a cusp. Does it have a derivative there? No. However, it's a local minimum. So the derivative does not exist at that point. The function is defined at that point. The function exists, but the derivative does not, which means it has a critical number there because the derivative does not exist at the point where the function exists. So then it has a cusp. That's why we know it's not differentiable there. Therefore, it's still a local min. It happens in this case to be also the absolute min. Okay, so now we're going to pick some functions and determine their critical numbers and decide whether those critical numbers change into max min or not. No, we don't. So we have to study the sign. Yes, we don't know that. We don't know. We always have to study the sign. In the situation in which the derivative is 0, and in the situation in which the derivative is undefined, where the function exists, is defined, we still have to study the sign. If we don't study the sign, we cannot draw any conclusion. Very good question. So that's exactly what we're going to do right this moment. So on page 281, I'm going to start with a simple one like 30. On page 281, we have f of x equals x, I think it's the third, plus 6x squared minus 15x. My glasses are too strong for this small distance here. Okay, perfect. So the question here is, find critical numbers. What type of function is it? It is polynomial, very good, degree 3, perfect. So let's find the derivative, which is 3x squared plus 12x minus 15. Would you agree with that? Good. Question. Does this function have critical numbers coming from f prime being undefined? No, of course not. This is a quadratic function is always defined. Does it have critical numbers coming from f prime being 0? I don't know. I haven't determined anything yet, right? So I'm going to say 3x squared plus 12x minus 15 equals 0. Of course, I'll divide both sides by 3, and I get x squared plus 4x minus 5. And of course, I'm going to try to factor. And when we factor, what do we get? When we factor, we get x plus 5 and x minus 1. So then we get x equals negative 5 and x equals 1. So we know this function has two critical numbers at negative 5 and 1. So now we're going to go back to a table, pretty much the same table we used before, but this time we're going to add more stuff to it. So f prime and f of x. Now you can choose the order you like. I prefer to put the derivative first, and then the function, and then at the end you'll see what happens in the next section. I'm going to add one more thing to it. But of course you can decide or create your own table. Whatever it is, just summarize the information somehow. Okay. So I have negative 5 and positive 1, and of course 0 and 0, because the derivative is 0 at that point. And now I'm trying to study the sign of the derivative, because these critical numbers may or may not turn into max min, but I will not know before I study the sign of this expression. It's a quadratic function opening upward. You can plug in numbers, but I think it's easier if you think in terms of this is a quadratic function opening upward and crossing the x-axis at negative 5 and 1. So what is the sign between negative 5 and 1? Opening up, because it has a minimum, the leading coefficient is positive. So it crosses at negative 5 and 1. So what will be the sign of the function between negative 5 and 1? Of course. And what will be the sign outside, to the left of negative 1 and to the right of 1? You don't have to do that. Just punch in a number. So then I plug in negative 5 in the function. I plug 1 in the function because I need these values. So let's go to the graphing calculator. Punch in y equals x to the third plus 6x squared and minus 15x. And then second in table. And I want negative 5. Oh, yes, of course. So I want negative 5, and I want 1. So the answers are 100 and negative 8. I would like us to determine the limit of this function because I want to put something here when x approaches negative infinity. I would like us to determine the limit of this function because I want to put something there. And you'll tell me what I should put here. Nothing matters but the most powerful one at infinity. Everything else is too small to mention. So when x approaches negative infinity, where does this go? It's negative infinity to the third power, which is, of course, very good. And when x approaches infinity, where does this go? That's why we studied limits first before this. At this point, I have to make sure that these two rows work well together. If they don't work well together, I have an error somewhere. So let's give it a shot. What does the function do before negative infinity and 100? From negative infinity to 100. It must go up. Would you agree?
Yes.
From negative infinity, is that supported by the sign of the first derivative? Is that supported by the sign of the first derivative? So the function is indeed increasing, no questions. Between 100 and negative 8, what does this function do? Yes, is that supported by the sign of the first derivative? Perfect. What does the function do between negative 8 and infinity? Is that supported by the positive sign of the tangent, the slope of the tangent line? Is that positive? Correct. So then, only now, I can conclude that this point, negative 5, 100, because the derivative changes sign, and it's either 0 or undefined, is definitely a what? Very good, local max. And now I can conclude that 1 comma negative 8, because the derivative changes sign from negative, 0, positive, or negative, undefined, positive. This must be a local min. So this is the mechanism. First, we determine the critical numbers. Then we create a table. Then we study the sign of the derivative. And then we conclude. If the derivative changes sign, add the critical numbers from positive to negative, that is a local max. From negative to positive, that is a local min. And this is something also called the first derivative test. The first derivative test. When f prime of x changes sign, at critical numbers, those become max min. The first derivative test basically says when f prime of x is greater than 0, f is increasing. When f prime of x is less than 0, f is decreasing. Okay, so I would like to work some more on other problems in which we determine critical numbers and whether the function has a max, local min, and also we're going to look at